So in example 3, it says because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given by S of t equals negative 0.81 t squared plus 2, where S of t is the height in meters and t is the time in seconds. What is the ratio of the Earth's gravitational forces to the moon? All right. So for this, we pretty much want to know what's going on, right? So the Earth's gravitational force is pretty much, as we know it before, is negative 9.8 meters per second squared, right? That's Earth's gravity. So on Earth, the object would be falling by S of t equals negative 4.9 t squared plus 2. All right. And then S prime of t equals v of t, which would be negative 9.8 t. And of course, S double prime of t equals v prime of t, or a of t, which is equal to negative 9.8. All right. So now that's the Earth. Then let's talk about the moon. So let's talk about the moon over here. So on the moon, the position function S of t is equal to negative 0.81 t squared plus 2. And then S prime of t for the moon would be equal to negative, or b of t, which would be negative 1.62 times t. And then finally, our acceleration, S double prime of t, which is v prime of t, or a of t again, is equal to negative 1.62. So now what is the ratio of the Earth's gravitational force to the moon? So how fast is it accelerating when it hits the floor, right? So we know that's negative 9.8 here, and we know it's negative 1.62 there. So we would do negative 9.8 divided by negative 1.62. And this is approximately equal to 6.049. And then this number tells us that the Earth's gravity is 6 times more than the moon, all right? At least. So Earth's gravity is 6 times more than the moon. So if you weigh 120 pounds here on Earth, that means that on the moon you would only weigh 20 pounds. Okay. So we challenge the second derivative. We want to find y double prime of t. So when y of t is equal to cosecant of t. Now for this one, what we want to do here is pretty much, it's our last problem. So we want to do is y prime of t first, right, as always. And then again, just you guys can look back in your notes and you can remember that the first derivative of cosecant is negative cosecant of t times cotangent of t. All right. Now, in order for us to find the product rule, now we're going to have to find the second derivative, we're going to have to use a product rule, right? So y double prime of t equals, right? So we have negative cosecant of t. We have cotangent, that's the t right there, of t. And then the first derivative of negative cosecant, again, that will give us negative cosecant of t, cotangent of t, right? Actually positive. And then the first derivative of cotangent, that is given to us by negative cosecant squared of t. And then again, draw your fish. So that was going to give us negative cosecant times negative cosecant squared would be positive cosecant cubed of t. And then we have plus cosecant of t times cotangent of t. All right. And then we can clean it up a little bit just by factoring out a cosecant. So y double prime of t equals cosecant of t times cosecant squared of t plus cotangent of t. And we're done.